Okay, so today's talk, you don't care who I am, you care what I have to say, right? So what I'm going to talk to you a little bit about what developers should know about computer architecture. As a rough agenda, we're going to go over why developers should know a little bit about computer hardware design in the first place, like why is this relevant? Doesn't the compiler take care of everything? We're going to talk about memory and disk latencies and how that can affect the performance of programs. We've got some examples in there. We're going to talk about the way modern CPU pipelines work. If you're familiar with that already, then you're probably not going to learn anything because I'm going to come at it from pretty high level. My goal is to target high-level programmers who have never really thought about how the hardware works. And then we're going to have a section on developing for parallelism. What does that mean? How does that change what you need to do? What are some of the pitfalls that you can fall into in terms of kind of destroying the performance of things rather than taking advantage of multiple cores or multiple CPUs? We're going to summarize with some lessons learned. So let's get started. Okay, first off, why should developers care about what the hardware is doing? Doesn't the compiler in the high-level language, don't they already take care of that? At least that was my perception. You know, compilers are pretty good at optimizing code these days. So why do I need to know, how memory layout works or how the CPU pipeline works? Well, modern compilers are amazing. They can do lots of work that you don't explicitly ask for. Like they can unroll loops, they can remove branches that they can move to branchless instructions. They routinely reorder or change instructions so that you can, so that as long as it doesn't affect the output, so that you're more optimized in how you use the CPU pipeline. You can even automatically vectorize code. So the compiler will detect if you have SIMD modules, it will detect, oh, we've got the opportunity to process this vector of data 4 items at a time, and it'll do that for you. You never need to know how to do SIMD. SIMD is single input, multiple data. So it's a way to, it's vectorized, so any GPU program is going to use SIMD programming. You're basically processing vectors of data item by item in chunks. So modern compilers are amazing, but they don't do everything for you. They don't own your algorithm. They don't own your data structures. For any Angelinos here, this is the St. Francis Dam. So I don't know if any of you know this story. You do? Okay, so the St. Francis Dam, it's up one of the canyons near here. It was designed and built by William Mulholland, eternalized in Mulholland Drive in the Mulholland Dam, which was another dam built by this Irish guy. So sorry about that. So it was a British-Irish self-taught architect who was very active in designing the water system of Los Angeles. This dam was built in 1927-28. And the dam didn't really take account of the substrate, right? The dam was not designed with an understanding of how the rock underneath was made up. There were several tests, and Mulholland, to his credit, took absolute full responsibility for it. It ended his career when this dam collapsed. It killed 431 Angelinos. It collapsed in 1928, right before the Great Depression. Part of the valley in which the dam was built was schist, which moved a little bit under the pressure of the concrete, caused cracks during the construction. It passed an inspection 12 hours before it collapsed. So this is just a cautionary tale. If you don't take account of what's happening underneath what you're building, you can have bad results. Hopefully this is not going to happen with your code, right? But you never know. So, algorithms, data structures, deployment choices, these matter for your application's performance. So it's important that you understand how what you're doing at the high level translates into what happens at the low level, particularly if it's going to dramatically impact performance. In general, you want to swim with the current. In this presentation, we're going to cover a number of hardware behaviors that might be invisible to you as an application developer, but they can be the silent performance killer for your application. They can cause your code to run 10 times, 100 times, 1,000 times slower. By gaining awareness of the underlying behavior, you can just write more optimal code. You can take advantage of the hardware and just make it easy for the CPU to help you do what you want to do. So we're going to cover three big topics: memory, locality, and data coherence, data access patterns, modern CPU pipelines, and coding for parallelism in multi-core or multi-host environments. Okay, so let's get started. Before we get into the content, I do have to talk a little bit about Ampere, but it's only just an introduction to show what a modern CPU looks like. When I talk about coding for the cloud or coding for a modern CPU, what do I mean? This is the Ampere 1M, it's our latest product. It's up to 192 cores at up to 3.6 gigahertz. You get, on each core, you get 16K of L1 instruction cache and 64K of L1 data cache. We'll talk about those a little bit later. You get 2 megabytes of L2 cache per core, 64 megabytes of system level cache, that's cache shared across all of the cores on a single socket, and 12 channels of DDR5 memory, up to 1.5 terabytes of RAM. And we also have some vector units per core, 2 128-bit vector units for SIMD calculations. Right, so this is what I'm going to use when I do latency figures here. I'm going to be citing the figures for Ampere. It's just because I know what they are for a start. But this is like when we're talking about modern CPUs and when we're talking about coding for parallelism, this is what you get in the cloud these days. I do not know what the TDP is. I do not know what the power consumption is, but I know that we're very, very competitive in power consumption because that's kind of the core. We're an ARM64 CPU. So that's kind of one of the core reasons why we believe ARM64 CPUs are kind of, the question was, what's the power consumption of that CPU? Power consumption is like power per core, but even power per socket, we're very, very competitive with anything out there. It's much lower than x86. And that's one of the reasons why we think this is kind of the future of the data center, is if you put a CPU that big, that's an x86 CPU, you have to account for heat, you have to account for cooling, you have to account for airflow or water flow through the server. You're putting fewer cores per rack because you have to leave empty spots for heat. I don't know if anybody have worked in a data center, but like the classic cold aisle, hot aisle, you need to account for the airflow that's going through these things. With Ampere CPUs, you don't have that problem, so you fill up your racks. You can have 42 servers in a rack, standard size rack, which means that you've got more cores in your data center, which means you're building fewer data centers, which means you're putting less pressure on the grid, which means there's a whole bunch of good stuff for CSPs, but it's also good for customers because your CSPs are renting you those cores cheaper. Anyway, he asked. I wasn't going to go into the sales pitch, but there you go. That's why we think ARM64 CPUs for the cloud are really important for the future. Let's get talking about some of the things that you need to know as a developer. So we're going to start with memory and disk latencies. So to make this a little bit more concrete, something that you can identify with, I said to myself, how can I turn nanoseconds, microseconds, and milliseconds into something that's meaningful to this audience? So since we're in Pasadena, I'm going to take a local landmark as a reference. We're going to take the Rose Bowl, the Pasadena Rose Bowl, and we're going to start from the 50-yard line. And to illustrate time taken, I'm going to use light time, right? So a meter and so 1 light second is 3 billion meters, right? So it's 3 billion meters per second, 1 light second. We're going to take access time to different levels of cache or memory as light distance. And I'm going to ask you all to guess how far light can travel and the time it takes for data to load. And I'm going to give you a freebie. If you are accessing layer 1 cache, you can barely see the red dot in the middle there because loads from L1 cache are fast. They're about 1 nanosecond. So 1 nanosecond is 1/3 of a meter, 30 centimeters, right? About a foot. So you're still basically at the halfway line. Maybe if we're doing this when there's a football match going, and the ball is placed on the halfway line, you're about like you can just about get outside the football, right? That's the kind of scale we're looking for. But remember, you only get 16K of instruction cache and 64K of data cache. So iCache is where your program lives. Data cache is where data structures can live that are accessed. So you've got small amounts of that data. What that means is that if your data that you care about on the fast path of your application is less than 64K, access to that data is super fast, but you don't have a lot of it. Okay? Now, moving from L1 cache to L2 cache, how far, who wants to guess how far we get away from midfield? The sideline? Okay, anybody else want to guess? Middle of the city of Pasadena? Stadium height? Okay, so outside the field, more than 100 yards, a 20-yard line I heard. Well, so those are all good guesses, but they're a little bit pessimistic. We actually get about, so it's 3 to 10 nanoseconds, on average about 5 nanoseconds. So we're talking about 5 feet, 2 meters, 2 yards, right? So light has now traveled between 1 and 3 yards, so let's say 2 yards. So you're surrounding your center and your defensive linesman maybe, right? It's not too far, but your arm's reach from the ball. So even though like layer 1 to layer 2 is slower, it's 5 times as slow, and you now have 2 megabytes per core. So if you can fit your hot path data in 2 megabytes, you're guaranteeing that your access time is going to be still pretty fast, right? Next up, we've got the system level cache. This is a shared cache by all of the cores. So you've got some bus latency, right? Because you've got mesh interconnect between all of these cores with their local memory. But if you're going to the system level cache, it's a little bit slower. Anybody want to guess how many times more slower? Twice as slow, 20 nanoseconds. 5 times as slow, so that would be 25, 30 nanoseconds. And it ends up being somewhere between 10 and 40 nanoseconds, so about 30 nanoseconds is the average. At this point, you've got, so we're gone past 10 yards away from, we're now, it's about, I think, 15 yards, give or take, 12, 15 yards. So we're now past the 40-yard line in either direction. So again, thinking about Ampere 1s, you've got 64 megabytes of this per socket. So that's shared across up to 192 cores. So you don't get a lot per core, but you also have the ability to define policy so that which cores get access and which cores get fast access to the system level cache, and you can deny access to the system level cache to certain cores. So it's you do have ways to tune this, but you've got a lot more data. This is still, I think, pretty fast, right? Okay, so now we're gonna go to the next one, which is SD-RAM, right? Are we still on the field? Hold on. This is skipping a slide. Why do I not have an SD-RAM slide? Yeah, but with SD-RAM, you're about 80 yards. So SD-RAM, you're talking about 100 to 150 nanoseconds. So it's about 5 times slower than this. So where we're 15 yards, 5 times, we're about 75 yards. You're in the end zones potentially, certainly sideline to sideline. I've kind of buried the lead. Now if I now go to the next fastest storage medium, it's local attached NVMe solid state disks, right? Okay, at this point, right, let's say we've got 100 yards for SD-RAM. How far away from the center field are we with NVMe? NVMe is basically storage, is basically RAM, right? It's a little bit more than that. It's 20 to 120 microseconds, so we've changed order of magnitude. We've gone from nanoseconds, 120 to 150 nanoseconds. We've now gone to 20 to 120 microseconds. Now, we've got a lot more of it. We've got hundreds of gigabytes of this stuff, if you have money and bought some before the prices went through the roof. That's also true of SD-RAM, by the way. But latency times for fast NVMe disks are in the tens of microseconds. So in terms of landmarks from here, in the optimistic case, you can get to the JPL. In the pessimistic case, you certainly have time to get to Burbank Airport or the Hollywood Hills, right? We're still inside LA. You've now kind of surrounded Pasadena, right? I've gone a little bit too fast. The next fastest, I've got two options to offer, and I'm going to do a pop quiz. Which one of these do you think is faster? Local attach spinning disk or local area network attached SAN running NVMe SSDs? The SAN, yes, it is, and it's quite a bit faster. So SSD powered SAN, we're now up to hundreds of microseconds. It is another 5 times slower. So we now have tens or hundreds of terabytes. We have storage arrays that can basically be arbitrarily large. But you're about halfway to San Diego at this point. Entire Los Angeles County is surrounded. You're now in like Santa Barbara, northwest, or you're in what's that town down there, Carlsbad in the south. You're quite a bit away, right? We're talking about 40, 50 miles. Next up, if I am using spinning disks, if I'm using SATA disks, how far, anyone want to care to wager how far, not wager, but guess, how far light can travel in the time it takes me to read from a spinning disk? Las Vegas? DC, New York? Who said New York? Who thinks New York is right? Who thinks Vegas is right? Yeah, you can get to Hawaii or New York. You can get to we're talking about. I could swear these slides were. Am I working on an old version? Anyway, we'll flow with it. We'll go with it. You can get to the Empire State Building easily, right? We're talking about 5 to 15 milliseconds of latency. So we're talking about another order of magnitude, right? Another 2 orders of magnitude from. So just the spinning disks, you have platters, you have a mechanical head that's seeking to read from a certain area. If you need to go to on-disk swap, for example, your performance takes a hammering. At this stage, the scales have gone from nanoseconds to microseconds to milliseconds. So by the time your data is loaded into your hard drive, light could have had the time to reach New York. And in terms of lessons learned from this, where you read your data from really matters. The closer your data is to the CPU, the faster your reads are. So you want small, fast, and close to the CPU for hot path data where performance is critical. And in terms of orders of magnitude, DRAM is 100 times slower than L1 cache. NVMe is 1,000 times slower than, is 1,000 times slower than DRAM? No, 1,000 times slower than L1 cache. And traditional hard drives are another 100 times slower than NVMe. So 100,000 times slower than reading from cache. That's a massive performance hit, right? If you have to read from disk, it's a performance killer. So what do you do with that information? How can you make sure that you're using algorithms and data structures that allow you to have that hot path data be efficiently used as part of your program? So designing hot data to fit in cache, processing large data sites in cache-sized chunks, using algorithms that allow you to do that, cache by chunk, that's going to be important for application performance if performance really matters, and we'll get to that a little bit later. Okay, next, let's move on to how data actually moves around inside your system. When you read a byte of data, you're not moving a byte of data into cache, right? The smallest unit of memory transfer is a cache line. I've used a carton of eggs here, but it's like you don't move data byte by byte. You move data chunk by chunk. The minimum amount of data that gets moved around in cache is a cache line. Cache lines are 64 bytes. So when you read from a memory location, that memory location is first in RAM, right? If the data is actually on disk and needs to be loaded into RAM, it's going to be loaded into RAM. That's called a page fault. That's a slow operation. Once it's in RAM, you seek to the specific location where that memory that you care about is, and you look for the boundary-aligned 64-byte chunk of data, and that's what you read into your L2 and L1 cache. Why does that matter? A cache line is 64 bytes of memory, and if a cache line is in cache, reading it or any of its neighbors that are already in cache is essentially free. It's 1 nanosecond for access time versus 5 nanoseconds or 150 nanoseconds or a couple of microseconds. If a cache line is already in cache, if a cache line is not in cache, the whole line is read from DRAM before data is loaded. And the way that works is you have a memory controller on your CPU activates a line of RAM. You have the way RAM activation works is you've got a first operation, it finds what row. RAM is laid out as a 2D array of capacitors, basically. They're either capacitors are loaded, in which case it's a 1, or they're empty, in which case it's a 0. And it finds the right row. That operation has a certain cost, and then it finds the column inside the row where the cache line starts, and that operation has a smaller cost. So if the row is already open, you get an optimistic, like maybe 50 nanoseconds. If it's not open, then it costs about 150 nanoseconds to read from RAM. So your memory manager is also kind of smart. It looks at how your program is accessing memory, and if your access patterns are predictable, it will automatically read in lines that it expects you will need in the future. If you're wrong, that has a cost, right? You've loaded memory into RAM that then gets evicted and something else needs to be loaded in instead. What that means as a programmer is that cache lines are prefetched based on data access patterns, and predictable access patterns mean that you're going to be using that data more efficiently. If you do sequential access of memory across contiguous blocks of memory, then basically your average read time is going to be closer to 1 nanosecond than higher, right? And data structures really matter for this. If you're a C++ programmer, if you're using arrays or vectors, those are fast, those are contiguous data blocks. If you're using on C or C++, or really any language, kind of binary trees or linked lists, those data structures essentially jump randomly around in memory because you've got a pointer to the next thing is part of the data structure. And every single read of an element of a linked list is going to cause some kind of cache eviction and loading in a new line. So arrays and lists outperform linked lists or binary trees. Again, I'm not saying that you can't use or you shouldn't use those data structures. What I'm saying is if you're in an area where performance is critical, you want to make sure that you're optimally using all of the data that you load into cache. You want to make sure that every cache line you want to get 64 reads, right? You don't want to be reading 1 byte out of a 64 chunk and then reading another byte out of a 64 chunk and doing that over and over and over again. That's optimally poor performance. You want to get optimal performance, which means using that sequential data structure. So this is not just theoretical. Let's take one example. If you're doing image manipulation, I used to work on the GNU image manipulation program. Commonly in graphics programming, what you're going to have is the image is going to have 3 arrays, or 4 arrays, depending on how many color channels you're using, with an array for the red data, an array for the green data, an array for the blue data, and an array for an alpha data. The reason why we store it that way is because you can optimally do a lot of image manipulation algorithms by processing chunks of those data. You can do that SIMD because the data is laid out in memory already. You're just passing in a new address and you're adding 64, adding 64, adding 64, whatever. So game developers routinely store image data in an array per color channel because it allows them to efficiently process that data using SIMD. This is called, by the way, in the game world, this is called data swizzling. If you're looking for, if you want to look this up. So laying out data that you really care about the performance in these contiguous data structures is kind of something that's real life performance engineering. Okay, so we're going to check how much this matters, and it's going to be hopefully interactive again. I'm going to take I've generated 1 million entry matrices, 1024 by 1024. So an A matrix and a B matrix, we're going to multiply them together. So each entry in the C matrix is going to be a sum of AIK times BJK. So we're going to go across the rows of the matrix, and we're going to go down the rows of the second matrix. So this is what we're doing. We're multiplying two 1024 by 1024 matrices. The code for this is super straightforward. This is too small for you to read, which is my fault. But the naive method goes for we're going to go for each ij in the C matrix. So we're going to traverse the C matrix row by row by row. For each entry in the C matrix, we're going to process a row of the A matrix and a column of the B matrix, right? So that's the naive method, is we go so the inner loop is K, which goes across a row and down a column. The second method we're going to use is column first. What that does is we're going to change the order. So instead of going across the C matrix first, we're going to do as our inner loop the column of the inner loop is going to be the column of the C matrix and the column of the A matrix. The outer loop is going to be our J, which is the column of the B matrix. Okay, and then the third, we're just going to change the order another way, and we're going to do row first. So we're going to change the order so that we do the row of the A matrix, the row of the B matrix, and the column of the C matrix. I'm messing this up, but. Like, the point is, the only thing that changes here is the order of the loops ijk. Okay? I was going to ask. So let's just jump in. The consequences for performance are dramatic. Ensuring that the inner loops are following row order for all of the major matrices, right, means that for each entry, so in the naive case, every element of the C matrix we're calculating it, and then we're moving on to the next one. In that naive case, we were getting 126 seconds on a single Ampere-1 core. If I do the worst case, which is the column first, as much as I can, it's actually not that much slower. It's 146, 147 seconds. So those were both getting really hit by cache line loads, right? Because every single entry in the C matrix that I'm calculating is loading different cache lines every time I go down to a new row. If I only just changed the order so that for each member of the outer loop, I'm going across two rows. That's the only change I made, right? The numbers go down to 8 seconds total, right? So 126 or 146 to 8, that is a 20x time saver, right? This is for a fairly simple mathematical operation, right? By the way, there are faster and better ways to multiply matrices, and we'll talk about those a little bit later. I reference them, but I'm not going to go into like tile-based matrix multiplication. But I will talk about that in terms of pointing you in the direction of places where you can learn more. So far from being a minor concern, this has a dramatic impact on the performance of something like matrix multiplication, which is key to, as we all know, AI, right? So this is the kind of thing where you really care about the performance of your application. So how you access data matters in addition to where you access the data from. Sequential access of contiguous data is fastest. Cache line misses and page faults can have a dramatic impact on application performance. and putting that into practice. You want to make sure that for the performance critical, and I'm kind of repeating this because we'll talk about premature optimization at the end, but for the performance critical aspects of your application, you want to make sure that you're using data structures with flat data types, so everything's the same size, so you're not doing arrays of structs that are contiguous in memory. And you want to access those data types sequentially to optimize for hardware prefetch so that your CPU memory management module can like make sure that data is ready for you when you need it.
Another way of putting it, though, would be how you access it changes where you access it.
How you access it does change where you access it. Indeed. Yes. So this gentleman said, isn't it like how you access it changes where you access it from? And that's correct, right? If you access data in a random manner, basically, you're going to be going to DRAM an awful lot, or disk, potentially. Okay, let's talk a little bit about modern CPU pipelines. It's possible to, modern CPU pipelines, there's process multiple instructions at the same time. So this may be old hat or knowledge that everybody here knows already, but instructions are loaded by the CPU into, I'm going to get in trouble here because I'm probably going to be wrong, but I think the ALU. So they're loaded from memory. Instructions that are loaded from memory are being loaded from iCache, which we saw earlier. That's 16 megabytes per core, 16 kilobytes per core, excuse me. In another stage, those instructions are decoded, so they're prepared for execution in terms of reading from registers that need to be read from. Then you've got the execution stage where the instruction is executed. Then you've got a memory stage. So if the instruction is a load or a store or requires some access to memory, memory access happens in stage 4. And this is a simplification. There are CPUs that have different pipelines. This is just kind of a standard RISC pipeline. And then in the 5th stage, you've got write back. So any results of that instruction are written back to registers so that they're available. And then the instruction is retired. So optimally, you can have 5 instructions being processed at the same time in different stages. That's what's happening in the green column here. However, each one of these stages can stall, right? If you're reading instructions and the instruction is not available in iCache, then you can end up going to main memory to get the instruction that you can decode. And so you're going, instead of a 1 nanosecond read, it can be a 150 nanosecond read if your main memory is busy. Similarly, on memory writes or reads, if the memory is not available in your D-cache, then you're going to be going to main memory or disk, and that can be a very costly operation. So you can stall the CPU pipeline in a number of ways. And one of the ways is branch prediction. So some of you may have heard of branch prediction, or in the context of Spectre and Meltdown. This is what we call side channel attacks, right? Basically, you can access some kind of indicator to what would have been loaded in the branch predictor, so that you can see something that never actually happened, but that can reveal data about what's going on in the CPU. I don't fully understand it. I have several friends who understand it a lot more, but this is the mechanism that's used. Basically, modern CPUs are going to have, like any program is going to have branch points. You know, if this happens, then do this thing, otherwise do this other thing. And because what you're doing is essentially, you want to keep that pipeline full. You want to make sure that you're loading what's the next instruction that's going to execute. And inside the CPU, you have the branch prediction module. Basically says, oh, I see a branch coming up in 3 instructions time. Based on what I've seen in the past, I predict that this branch will be taken, and you load that instruction, and you're getting it into the start of the pipeline. Now, if by the time that branch instruction is actually being executed, your prediction is wrong, you throw away all of the work that you've done in preparing that instruction, in reading registers that are required, in getting it ready for execution. You throw all that away, and any other instruction that you've loaded after that, and you have to restart your pipeline. Oh, okay, I was wrong, branch misprediction. I throw everything away. What's the next instruction? I'm loading it from iCache. So the cost of the prediction, if it's wrong, can be up to 20 cycles. On an Ampere 1, we've got an average branch misprediction cost of 10 cycles, which is very impressive industry-wide. But branch predictors on current hardware can achieve 95 to 99% accuracy on typical workloads. And you will see some numbers in just a second. The predictor maintains a history of recent branch outcomes and basically is very good at predicting what comes next. So you want to keep that prediction success rate as high as possible. 99% and up is what you're aiming for. However, programmers sometimes do stupid things. And the way that you code, the way that you code can make it more likely that you're going to have a branch misprediction. There are a few dependencies. There are a few things that happen in CPUs, right? You can have data dependencies where an n+1 instruction is calculating something that's needed by the n instruction, and you can't execute that n instruction until the calculation is completed. That stalls your pipeline at the execution stage. You can have control dependencies where the outcome of instruction n changes the instruction n+1 to be executed. Branch misprediction, we already talked about that. I'm not going to spend any more time on it. So here are some of the ways that developers can break your pipelines. If the CPU is pretty smart about branch prediction, what can I do about all this? Or are there things that I do to make it better or worse? And you can definitely make it worse, right? 3 ways that the pipeline stalls. I've talked about back-end stalls. That's when you don't have memory that's required already in cache. You have front-end stalls. That's when your instruction that's required is not yet in iCache. That happens, for example, if you have a lot of functions. You don't necessarily think of a function call as a branch. It's a branch. You're going to a new part of memory. That can happen if you have, for example, if you have a C++ code with a lot of polymorphism. If you have multiple definitions of a function that are rendered at runtime, that's essentially something that the CPU can't predict, right? It doesn't know what the next instruction is based on what you've been doing in the past. So you can cause instruction cache misses with bad function etiquette, especially on the hot path. And branch misprediction, you can make it hard for the CPU to predict what comes next. And we're going to go into an example of some of the ways that, one example of how you can make branch prediction difficult. But yeah, so if you have lots of small functions that are called through function pointers, if you have lots of polymorphism, if you have lots of, these are things that can cause higher branch misprediction rates. So here's one example. We're going to generate a list of 10 million random numbers between 0 and 100, floating point numbers. And we're going to count how many numbers are under 50. Right? If the number is under 50, add 1 to the count. If it's over 50, add 1 to the over 50 count. Just to have a little bit more time, we're going to iterate that over that 20 times. So what you're going to see here is 20 times 10 million, 200 million. We have 200 million branch operations, and we're going to see how many successful predictions we have versus unsuccessful predictions. On the first time through, we're going to do it on random data, just straight out of like the random number generator. On the second time through, I'm going to sort the list and do exactly the same operation, right? It's the same code being run on 2 different data files. One where it's random, one where it's sorted. And I'm going to use perf to count the time and the branch predictions for the operation. Okay, on the unsorted data, so I delay 500 milliseconds. That's just to allow the Python VM to start up, and I'm kind of not counting Python startup. I'm looking for how many cycles, instructions, branches, and branch misses I have. I'm going to pin this to a single core, just so that it doesn't move around. Like, I don't want the kernel to be doing anything smart. So what I get out of my count is, I don't know how many digits are in that. 303, 6, 9, 35 times 10 to the 9 cycles. I end up with, 2.5 instructions per cycle, which is, we were talking about you can execute up to 5 instructions per cycle. This is pretty awesome. Like 2.5 is pretty good. We end up with 100 million branch misses, which is 1.92% of all branches. There are, in general, and this is kind of expected, we're running Python, right? This is the full Python VM. There's a lot of code that happens before my code gets even processed. So we end up with, I don't even know how many, 5 by 10 to the 9, 5 billion branches, 100 million branch misses. But 100 million branch misses is kind of what we were expecting from our data, right? 200 million comparisons, we were expecting 100 million misses, 100 million hits. Basically, we're flipping a coin. We end up with our total time being 11.2 seconds user time for processing this list, right? So branch miss prediction, 100 million, time 11 seconds. On the sorted data, I do the exact same operation, but I'm running on a sorted data list. What happens is, the first time through, it sees something close to 0. Next time through, it's 0.2 or whatever. And it's like, oh, I predicted under 50 last time. I'm going to keep predicting under 50. And then it hits 50, and it gets it wrong once. Maybe it gets it wrong twice. And then it's like, oh, now we're over 50, and it just predicts over 50 every single time. So we've gone from 100 million branch misses to 2 million, which is pretty much what we would expect. We've gone from 11.2 seconds to 9.7 seconds. So on a relatively simple piece of code, we're saving a second and a half on this particular algorithm, not by changing the code, by changing the way that we feed the data into it. So this is all in Python. There's a reason I use Python and not C for this. I talked about how compilers are amazing, right? If you do the same thing with C, compiled with the right optimization level, it automatically detects there's an if-else, and it uses a branchless instruction. It will use a ternary instruction. It will use some kind of method to say, okay, I'm going to do a test, and then I'm going to, like, it uses an instruction which doesn't use a branch, right? Which the CPU can then read sequentially. So we get an identical result with and without the sorted data, just because the compiler is awesome. So some of this stuff that I'm introducing to you here, compilers do help you take care of it if you've got -03, -04. The way it does it is pretty neat, and it's worth dwelling on a second. The C compiler does better because it can avoid branch mispredictions by avoiding branches. So for those of you, who here has heard of branchless programming? Got 2, 3 folks? Okay. We can avoid branches altogether by using branchless algorithms or language constructs. Here are just two ways to eliminate the branch in what we just saw. One is a ternary operator, which gets translated into different assembly instructions. So you go x less than threshold, under plus plus, or over plus plus if it's greater than threshold. Or you can use bitwise arithmetic. You create a Boolean that is this data element is less than a threshold, and then you add the Boolean to both the under and the over. If it's less than the threshold, the under goes up by 1. And the over doesn't change because the Boolean is false. If it's greater than the threshold, the under doesn't change because it's false, and the Boolean and the over goes up by 1. So there are a lot of branchless programming techniques. It's out of the scope of this talk. But if any of you have heard of the $1 billion challenge, anybody here for the $1 billion challenge? I recommend you go looking at it. Yeah, so something that came out of the Java community last year, I think. So there was a reference file of a billion rows, a billion row challenge, a reference file with temperatures from weather stations that had a billion rows of data in it. And you had to accomplish some task of the min, max, and average temperature for each weather station. And there was a kind of a reference implementation that was bog standard Java that took, I think, 140 seconds, right, to process the billion rows. And by the end of the competition, people had gotten it down to 3 seconds. The way they did that was some of the techniques were really interesting. It's just like we're going to load the data with a mem map and instead of reading rows. Some of the techniques are, we're going to skip the slow part of terminating the process. We're going to trick the program into ending the time, and then we'll do cleanup after. But the biggest gains were by moving to branchless processing of the data. So I strongly recommend you look at that. Branchless programming is a way to deliver maximum performance on the things where performance really matters. Sometimes, as a warning, some of the people I've talked about to this are like, yeah, but branchless code, sucks because it's hard to maintain, it's kind of confusing, and that can be true, right? If anybody who's seen John Carmack's inverse square root function, right? You know that like magic numbers kind of pop up out of nowhere and you don't know what's going on. You're kind of casting an integer or a float into an integer, adding a magic number or anding it with a magic number and then casting it back to integer. Yes, there are sometimes situations where you're going to make your code harder to understand, harder to maintain, but if you really care about the performance of that thing, if it's a thing you're running billions of times per second, then you want to make it as fast as possible. Okay. Warning. Don't fix what's not broken. Before spending a ton of time fixing something that will only have a small effect, you need to do some profiling. So this is a graph generated from an Ampere tool called the Ampere PMU Profiler, which basically investigates CPU events using the PMU, Performance Monitoring Unit. And it can tell you where you're losing time. Are you losing time in the front end because your instruction cache is not being hit well enough? Are you losing time in the back end because your memory is not being consistently or efficiently accessed? Are you losing time in your pipeline? Make sure that you're using tools that are available, like Perf, like the Ampere tool suite, to see what's going on in your application. Before you invest a lot of time doing things like improving the performance of the idle loop, which is kind of the classic example of premature optimization. Okay, so lessons learned. You can make it hard for the computer to predict the future. You can help or hinder your CPU branch prediction. Try and get out of the way. Getting out of the way means that your CPU, you're basically taking advantage of all of the engineering that's gone into your CPU. Inefficient programming that leads to poor branch prediction can slow down your program. Using branchless techniques or algorithms algorithms is going to reduce branch misprediction. And if you're doing any high-performance programming, if you're doing any GPU programming or SIMD, using SIMD modules on the CPU core, SIMD doesn't have branches. You're just processing bunches of data. So learning how to do things with bitmaps and processing data chunk by chunk has the benefit of automatically being branches, right? So it does require learning some branchless techniques. Okay, we're running out of time fast, so I'm going to just zoom through developing for parallelism. Why is this important? The cloud has kind of changed how we develop code and how we develop applications. We now have dozens of services or applications. Each have their own components. Each are running on virtual machines that can have lots of compute. Right? We talked about the Ampere 1, 192 cores. It doesn't make sense to run a single-threaded application on a 192-core machine. You're going to have one red-hot core and 191 that are sitting idle doing nothing, right? So the cloud has fundamentally changed the way application development happens. So there are a few techniques that we can use to make sure that we're taking advantage of all of those cores that we have at our availability. Coding for more cores is different. And here are just some of the ways. There are a lot of them. I really like this Ian Coldwater. There are a lot of them. First is you're going to be running, if you're using in a single application many cores, you're going to be using threads. I like a joke where, you know, a programmer had a problem, so they used threads, now they have two problems. Threaded programming is hard because you end up needing to be careful about critical areas of a code where you've got information shared between threads, right? So you need to have the appropriate level of locking, you need to have the appropriate semantics around acquiring and releasing data. And you can do, you know, we'll talk about this in a second. You don't have to completely lock data so it's only one thread accessing the data, particularly if everybody is reading the data and you only need to update it when it writes, right? So having the right level of locking is important for performance. Parallelizable algorithms. So we talked about the matrix multiplication earlier. You can do tile-based multiplication of matrices, which means that you've got small cache-sized blocks of your matrices, A and B, in cache. You're generating a block, an intermediate block, and then at the end, once all of the intermediate blocks are available, you add those in a certain way and you get your matrix multiplication C. So having parallelizable algorithms means that you can ship little pieces of a problem to different cores and aggregate the results when they're done. But that results in data synchronization issues. You need to make sure that there's no data shared across different cores. You've got mesh congestion issues where if you're shipping a lot of data between different cores, you can gum up the system basically and add latencies to your mesh congestion. I haven't talked about, and I won't talk about beyond this, NUMA. So NUMA is, it stands for Non-Uniform Memory Access, thank you. So if you have multi-socket systems, each socket is going to have a fast track. I think I actually have a slide on this. Each socket is going to have a fast track to certain storage, memory, peripherals, right, network cards. If a CPU core on one NUMA node tries to connect to a network card on another NUMA node to do network reads, the latency is going to be terrible because it's not on the fast path. But the main thing I'm going to talk about here is cache coherency and false sharing. So I don't know, who here has ever heard of false sharing? One. Nice. Good. You're all going to learn something. Excellent. Before we get into cache coherency, I want to just give credit where credit is due. None of this is original material. This is Scott Myers, who is an old-timer programmer. I strongly recommend the presentation CPU Caches and Why You Care by Scott. He goes into this in a lot more detail than I'm going to. I'm going to give you a flavor of it. But there's way more, and I recommend that you look into everything that's involved in parallel programming, and I'm going to link to some resources in the slides that will be available for you afterwards. But let's talk about cache cohesion. When cache lines are loaded into the CPU cache, if you have two threads that are using, that load something into CPU cache, they're copies of the canonical reference data, which is in main memory, right? There is only one reference in main memory. Everything else is a copy. So if multiple cores are using the same cache line, writing in one core needs time to propagate to main memory and to the other copies of that. So let's look at what happens as it happens. Let's say we have two cores, core 0 and core 1, who are accessing the same cache line. I'm talking about cache line because, again, that's the atom of how memory moves around in the system. Core 0 and 1 both get a read-only copy. It's marked read-only. It's marked read-only and shared. If core 0 writes to the cache line, core 0's copy gets marked for synchronization. Core 1's copy gets marked as dirty, no longer up to date. So core 1's copy is now marked as invalid, and an invalidation message is sent to any other cores that are using the same cache line. Core 1 tries to read the line from memory, but is stalled until it updates the line from either core 0 or main memory. Both cache lines then return to this status shared, right? So basically, when I write here, I can't read here until that write gets propagated. and its cache line is the scope. And I'm emphasizing that because you'll see why in a second. So this, there's a kind of a seminal Dr. Dobbs article from, I think, 2008 or 2007, by this gentleman, Herb Sutter, who describes this problem of false sharing. He describes a scalability issue that he came across. So, again, the code on the right is unreadable. It doesn't actually matter. All we're going to do is we're going to take a task. We've got a large corpus of data. We want to count how many times something happens in that corpus of data. And what we're going to do is we're going to break that down into 16 chunks. We're going to send a chunk to different cores. We're going to count in each core how many times that thing happens. And then we're going to add up all the counts at the end, right? The way that we do that is we have an array with 16 entries, core 0, core 1. So count with 0, count 1, count 2, count 3, up to count 16. And inside an inner loop, we're going to increment that counter every time we get a match on the thing we're counting for. So when you ran this on a 24-core machine, not a 16-core machine, but we're going to just run with it. On a 24-core machine, this is the performance he got, right? When he went from 1 core, reference 1.0 or 100%, to 2 cores, he actually lost 40% of the performance. This is not what you're looking for in scalable programming. It took until he started to gradually improve the performance as he threw more cores at it. It took until I think he gets to 16 cores before he's above 100%. So he's using 16 times as much compute, and he's generating what he could have done with 1 core. This is not good. And eventually, it gets to a point where performance starts to go down again when he gets to core 20, 21, 22, 23, 24. So this is, obviously something is wrong here. He made a change. Sorry, before we get into the how he fixed it, we're going to make a small assumption. Our array of integers storing counts is stored in a single cache line. So here's what happens, right? We've got our main memory, cache line, with our 16 counters. Core 0 gets a copy, core 1 gets a copy. Core 0 finds a match somewhere in the corpus of data, and writes its entry into entry 1 of the cache line. That marks the cache line dirty. Okay? At this point, core 1's cache line is out of date and is also marked dirty and needs to be updated with this new write. Okay, so at that point, the core 1 copy of the cache now gets marked stale until the core 0 write replicates. Core 1 has found a match and wants to update count 1. It wants to update the second entry in the array, and it can't do it because the cache line is dirty. So the cache line gets propagated, which takes a few milliseconds, I think. And then now core 1 can write to count 1. Okay, it's written to count 1, and that cache line gets marked dirty again. Now, note, they were not writing to the same memory location. They're writing to 2 different entries in an array. But because those 2 different entries in an array are in the same cache line, it completely stalls the program. So they lose all of the benefit of having multiple cores thrown at the problem. You make a small change. Rather than using array entries, you have inside each thread, you create a local integer that's just a count for that thread. After you've processed the chunk of data that's allocated to that thread, you set the array entry equal to the count that you end up with. Okay? By doing that, you've removed all of the intermediate writes. You're writing once per thread, so you're writing 16 times. All of those writes get synchronized. You add them up at the end when all of the threads complete, and you get the result. What Sutter found is that he went from what we saw earlier, that mess, to this, right? Adding 24 cores, he gets 24 times the performance. So what are the lessons to be learned from here? Be careful when you're sharing data across multiple cores. Attempting to modify a shared cache line on multiple cores will end badly. You need to have some awareness of any time you're sharing cache lines, because, as we've seen, it's a massive performance killer. So it does need a little bit more care. So what can you do about it? We have some really good techniques that have developed over time for parallel programming, and they're common lessons from microservices, right? Consider functional programming best practices. So this is kind of, generally speaking, shared nothing, immutable data, pure functions. So a pure function is a function that, when you call it, has no side effects, and like any changes it makes are own. It's given a task, it does the task, it communicates with other functions through messages. There's no shared data. You can use perf C2C, which I really like, to see if there are more load hits on modified memory than you would expect. So this is basically analyzing cache line locks. So in general, thinking about, well, I thought I had something on memory. This may be in here. So part 4, conclusions and lesson learned. Where you read your data from matters, and how you access your data matters. You can make it hard for your CPU to predict the future, and you need to be really careful when sharing data across multiple cores. So those are the lessons learned. What can you do about it? Again, keep your hot path data, I'm going to be insisting on this, keep your hot path data small and contiguous, and process it in a contiguous sequential manner. Use your data structures with flat data types that are contiguous in memory. Access those data types sequentially to optimize for hardware prefetch. Avoid a lot of, I don't think this is in the list, but avoid a lot of things like function pointers that are dynamically rendered at runtime, or polymorphism, particularly in performance critical parts of your code. Use branchless techniques in inline code to reduce branch misprediction. Compilers can help you here. And functional programming techniques will help for parallel programming. And I want to particularly call out to memory oblivious, I think it's cache oblivious programming. Cache oblivious programming. So if you're getting into the world where you're programming for performance with multiple cores or multiple machines, cache oblivious programming is basically, this is a set of algorithms for common high performance tasks that allows you to operate locally on data. So you process data by chunks, you can do things in parallel. Obviously important for AI, and it's particularly important with generative AI because you've got multiple transformer layers, multiple attention heads, and all of the rest. But most important, do not optimize before you're ready, right? Measure twice, cut once. Benchmark and characterize your performance issues before you start making any major changes. The biggest changes are going to usually come from very simple changes, choosing the right algorithm, choosing good data structures. And that is it. And I've gone a little past an hour, but if I have the indulgence of the conference, I'm happy to stay for a few questions. And while we're taking questions, I'll put up first. This is some resources on where you can join the Ampere developer community. Some information. We have an awful lot of information on performance engineering. We have a very, very high quality performance engineering team that communicates tuning guides about how to get the most out of your computer hardware, which is effective, which is both for like, it'll work on any architecture, but obviously particularly we give advice for ARM64. There's sample code, documentation, examples, and videos. We have a lot of information there, and I'm going to put up a list of resources at the end. So I'm happy to take questions.
I have the mic here for anyone who has a question, and let's thank Dave for a wonderful presentation. For any of you that still are attending the keynote, there is a keynote at 3 p.m. in ballroom D and E. I'm coming around with the mic for questions.
Yeah. Thank you all for coming, and like I said, I'm happy to stay for a couple of minutes for questions, but if you need to go to the keynote or want to go to the keynote, you can leave right now. You don't feel like you're hurting my feelings.
Does Ampere have any custom ports of various like linear algebra libraries like BLAS or anything like that that's optimized for your
So
device?
there is an Ampere performance, so we've got the Ampere AI optimized library, which is a set of optimizations for Ampere of PyTorch, Onyx, TensorFlow, Llama CPP. I'm not a... Are we recording?
Maybe I'm not AV.
Okay. Okay. I would like us to be...
You can take off the mic if you like, and everyone can move closer.
Yes. Yeah. I'd be happy to answer that question later with a little bit more detail. I think, yeah, we do have some. Yes.
Anyone else for question?
You mentioned there's a piece of software, there's a PMU monitoring solution that Ampere
Yes.
has. What is it called?
You can see the link, it's not a link. Ampere Performance Toolkit. We have a set of 5 tools, one of which is only available to customers for reasons that I'm not sure what they are, but we have the Ampere Porting Advisor, which gets your code working quickly on ARM64 processors. It basically tells you which versions of your tool chains and where you might run into issues with dependencies. It even looks at code and says, oh, you're using this header and this library. Those are not available on ARM64. So that's the Ampere Porting Advisor. We have the Ampere System Profiler, which is a curated set of reports that we generate using standard performance tools, things like MPStat and perf. Then there's the Ampere PMU Profiler, which gives you those CPU level reports. And finally, we have the Ampere Performance Benchmarker, APB, which basically runs a set of curated micro profiling suites, benchmarking suites, and encapsulates, the important part is it encapsulates all of your system configuration in the report that it generates so that you can share that with somebody else and replicate a problem, which like replication of performance issues is kind of the #1 problem that our performance team has had. Like a customer says this is slow and they're like, well, it looks fine to me. This is the tool that allows you to replicate a system configuration on another system and verify if you're seeing consistent performance. So those are the Ampere tools.
Thank you so much. Also, does it work on other ARM64 devices, or is it just...
Yes, they're all ARM64. They will work on every ARM64. And it's all open source, right? So it's on GitHub. Ampere Performance Toolkit, you can find it in the Ampere GitHub repository.
Thank you so much.
Thank you.
Anyone else for question? Anyone or comment or, you know?
Thank you very much. And thank you all for staying to the end. I'm going to let you all get to the keynote now. I've kept you long enough. Thank you.